So an annuity is a regular series of either deposits or withdrawals. So if you're in retirement, an annuity might be withdrawing a certain amount every month. But in this video, you're very far away from retirement. So we're going to focus on annuities as a way of saving or a regular series of deposits into your saving account. This is something that I highly recommend you do. So you can set up an automatic saving where you're automatically putting in a certain amount into your savings account every month. And it's super easy to set up with your bank, and it helps you stay on track with your saving goals. When life gets busy and you forget to save, if it's automated for you, then it'll actually happen, which is really helpful. So how does it work? Let's say you're going to deposit $600 each year. So your annuity is $600 and it's just yearly. And you have 5% interest compounded annually, and we want to know how much you'll have after 3 years has passed. So in your first year, well, you've just put in $600. That's how much you put in right away. The next year, after one year's gone by, you've earned 5%. So 5% of 600 is $30. So you've gotten this $600 has grown to $630. But you also add another 600 in every year. So the idea of an annuity is that the amount you put in your first year will grow with compound interest, but you keep putting that amount in every year, or this could be every month or every week, however you sort of set it up. Your next year, that 630 is now going to grow with interest on the interest. So we're going to do 630 times 1.05 to get how much that will grow to, which is $661.50. This 600 that you put in last year will grow with compound interest to 630, and you'll put in another 600 this year. All right, now in our next year, this just keeps going. So your $661.50 will grow with compound interest again, all the way up to $694.58. The 630 will grow with compound interest to 661.5. The 600 that you put in last year will grow to 630, and you'll put in another 600. So by the time you're in year 3, you'll have all of this, so we could add that all up. So our 694 plus the 661.5 plus the 630 plus the new 600 that you just deposited, and by your third year, you have $2,586.08 here. All right, so what is going on here? Well, if we look at each of these values here, this would be like the first term in a geometric series. This is like T1. This would be the second term, T2, right? But where the second term, if T1 is 600, the second term we're multiplying by the multiplier times 1.05 every year. So that's like our multiplier. This year would be the third term. Right now we multiply by 1.05 again. And this would be the fourth term. And notice what we're doing to find out how much you have after 3 years is we're just adding all of those numbers up. So what kind of discrete function is an annuity? Well, it's related to your geometric sequence, but it's the sum of that geometric series. We call them a series when we're adding them up. So it's actually the sum of a geometric series. So we're going to use that to figure out the formula for an annuity where you're saving. All right, so this, if you remember back to, I know it's been a while since discrete functions, but if you remember back to discrete functions, this is the formula for the sum of a geometric series here. So T1 is your first term. R is the multiplier, so in the last case that was 1.05. N is the term number, and S is the sum of up to term N. We're going to turn that into an equation for financial math. So T1, what would be T1? Well, that will be the amount that you deposit every year or every month, so that it's just the amount that you deposit on a regular basis. So into your savings account, on a regular basis. So in the question we just did, that was the amount you put in every year, but it could be an amount that you're putting in every month too. And we're going to call that actually P. It's kind of like your principal that we were talking about with compound interest, but it's a principal that you keep adding every single year or every month. You keep adding a little more P here. So what is R here? Well, that was the multiplier. If you remember from the example we just did, the multiplier was 1.05. And what we did to do that is we took the interest rate, little r, we turned it into a decimal, and we added 1 to it. So here r is the interest rate as a decimal. And it's actually the interest rate per compounding period. Oops, spelling that wrong. So per compounding period, and it needs to be as a decimal. So in the last case, there was just one compounding period per year. It was just an annual thing. But if you have to turn that into maybe a monthly compounding, then you would divide by 12 to get R, just like we did with compound interest. All right, so making those adjustments, that actually gives you your equation for an annuity, which must be this. So the sum that you have at the end will be how much you're investing every compounding period, so how much you put in every month maybe or every year. On the top here, we have r to the n, so replacing that actually with 1 plus little r. And n is how much time has gone by, so it's going to be t. And t, just like with compound interest, t will be the number of compounding periods. So that might be the number of years if it's compounded once per year, but if it's compounded, say, monthly, it would be the number of years times 12. All right, then we've got minus 1 on top. And all of this is divided by r here. So it's 1 plus r. And then minus 1. So you'll notice that that can simplify a little bit, right? We've got a 1 and then a minus 1. Those guys will cancel out. And I can simplify my formula to this. So the sum, everything you'll have at the end is P times 1 plus little r to the t minus 1 all over r. And that's our equation for an annuity. All right, let's try using that with an example. So let's say you want to retire with $1 million. That sounds nice. And you'd like to work for about 40 years. And you're going to be putting in a little bit into your RSP or maybe a combination of your RSP and your TFSA at 4% interest rate, say, and it's going to be compounded monthly. So let's write down our formula first. So our formula is this. S will be P times 1 plus R to the T minus 1 all over little r. What we're trying to solve for is P. We want to know how much do I need to actually put in my RSP every month. So P is really what I'm looking for here. The $1 million is how much I want to have at the end. So that's how much I want saved at the end. So that's going to be S. So S is $1 million. R is my interest rate, but be careful, R has to be my interest rate per compounding period. So this is compounded monthly. It's a 4% annual interest rate, so I have to take that 4% and divide by 12. So take your 4%, divide by 12, that gives you 0.00333, and the threes will just sort of keep going there. All right, T, that's the number of compounding periods. So you're going to work for 40 years. This is compounded monthly though, so it's going to be 40 times 12, right? So 40 years times 12 compounding periods per year is 480 compounding periods altogether. All right, we want to plug all that into our equation here. So S is $1 million. So plug that in. P, I don't know, we're solving for that. In these brackets here, we have 1 plus R, and R is 0.00333. Also the T, which is 480. And then we're going to minus 1 on top. All of this is divided by R, which is 0.00333. It's a good idea to keep even more decimals than I've shown here if you can. The more decimals you keep, just the more accurate your answer will be, and small deviations in accuracy can actually make a pretty big difference. So I'm keeping, when I do this here, I'm actually keeping the full digits, like all of the decimals for R in my calculator. I'm not clearing my calculator and retyping out 0.00333 and stopping there. I'm keeping sort of those repeating threes, so they're staying in my calculator. So I'll do that 0.00333, and the 3's going forever, plus 1. And then to the power of 480, the number of compounding periods. Then we want to subtract 1 from that, and that gives me that whole bracket on top. Then that's all divided by R again. So we'll divide all of that by R. And that gives me this here. So 1,000,000 on this side is equal to P times all of this stuff here plugged into my calculator worked out to 1,181.96. Then we can divide both sides by that. So we'll divide the million by that value, and we get P is $846.05. So if you would like to retire with $1 million in 40 years, and you happen to find a 4% interest rate, in reality, I mean, interest will change over your lifetime. It will go up, it will go down. Different products will do better than others, but we'll imagine we found 4%. Then what you would need to put in every month is $846.05.